Lecture 2, Matter and Energy, Redefining Reality.
Welcome to the second lecture in this odyssey, carrying us through science in the 20th century. And today's topic is the theory of relativity, or the special theory of relativity and the general theory of relativity, which we will discuss sequentially, but they really represent a single, a more comprehensive view of space-time, matter, and energy that we'll call occasionally the theory of relativity. 1905 was an astonishing year for Einstein. Among the papers that he published were three, each of which was epical in the history of 20th century science. One of them was on the so-called Brownian motion, something that had been observed for 70 years before Einstein, but never satisfactorily explained, and that is that very small particles suspended in a solution, if examined carefully, jerk around for no obvious reason and don't follow any obvious path. They just jerk around in what seems to be random motion. In the course of providing a theory of Brownian motion, Einstein managed to convince most of his fellow physicists for the first time that atoms were real. The chemical atom had been accepted as real by most chemists in the 19th century, but most physicists did not believe that atoms were real until the first decade of the 20th century. So Einstein's paper on the Brownian motion was quite influential on convincing his fellow physicists that atoms were real, not just an intellectual construct that was useful for solving certain kinds of problems. The second paper, which we will come back to in the next lecture, is on the photoelectric effect. Einstein explains the phenomenon that certain materials, typically metals, when exposed to light, give off electrons. We're familiar with this as photovoltaic devices today, but that's based on this photoelectric effect, which Einstein explained, and in fact, that's what he got the Nobel Prize for. He did not get the Nobel Prize for either the special or the general theory of relativity. Even in 1921, when he won the prize, they were considered too speculative to give a prize for. But the photoelectric effect paper of 1905 is one of the foundational papers of quantum theory. It really begins quantum theory. And yet Einstein published a third paper in that same year that was of fundamental significance for the course of 20th century science, and that is the paper that we call the special theory of relativity paper. In fact, the title was much more esoteric. It was on the electrodynamics of moving bodies. What is the problem that the special relativity theory came to solve? Well, there were really two problems. One problem that physicists shared and one that was Einstein's. The problem that physicists shared should have been a simple problem, but in the second half of the 20th century, using the wave theory of light, physicists tried to measure the speed of the Earth, the motion of the Earth in space. And every attempt to measure it came up with 0. Now, we knew that we could measure the Earth's motion relative to the sun, but given 19th century science, it should have been possible to measure the speed of the Earth with respect to space. In fact, Michelson, who I referred to as the inventor of the interferometer in the last lecture, invented the interferometer to use light waves in order to measure the absolute motion of the Earth with respect to space. So every experiment came up 0, and furthermore, every attempt to measure the speed of light discovered that the speed of light was the same no matter what you did, which is very bizarre. Nothing else in nature that we're familiar with has this characteristic. If you are traveling in an automobile on a highway, and an automobile is traveling towards you, you're traveling at 60 miles an hour, it's traveling at 60 miles an hour, you will measure its oncoming speed as 120 miles an hour. If you are traveling at 60 miles an hour, passing a car going 50 miles an hour, then you will measure that other car's velocity as 10 miles an hour slower than you. But light, no matter how you're traveling, no matter how you measure it, keeps throwing up the same speed, 186,000 miles a second approximately, or if you prefer kilometers, 300,000 kilometers a second. That was the problem that was common to all physicists. Why can't we measure the speed of the Earth? And what is this business with the speed of light? Einstein had his own problem. He was troubled by something so simple that you would ordinarily dismiss this as an elementary school sort of thing. What does it mean to say that two events happened at the same time? From the 17th century until 1905, when Einstein made it the focus of this paper, it was just taken for granted that you just see when two things happen at the same time. But Einstein pointed out that since everybody believes that the speed of light is limited, it's fast, but it's limited, in order for you to see that an event distant from you happened at the same time as an event near you, then you have to get a light signal from that second event. It takes time for the light signal to travel to you. So as a matter of fact, if you're standing in a place and you see something very close to you happen, and you, out of the corner of your eye, see that something further away is happening at the same moment, guaranteed that one didn't happen at the same moment. That one had to happen earlier because it took time for the light to travel to you. So Einstein took these two problems and he solved them in the special theory of relativity in a way that is very simple, reminding us of this idea of the emergence of complexity out of simplicity. Very simple theory, the special theory of relativity, but its consequences are tremendous. It rests on two principles, one of which had been accepted by physicists for 300 years. It's called the principle of the relativity of motion. When two observers are traveling at a uniform speed, there are no forces acting on their laboratories that are not the same in both laboratories, then the laws of physics will be identified by both of them to be the same. If you drop rocks off the Tower of Pisa and you come up with Galileo's equation, S equal 1/2 GT squared, and you do the same thing in New York, you're going to get the same equation. It's not going to be different. That's what's special about the special theory of relativity. It restricts itself to comparing the laws of physics in frames of reference that are moving uniformly with respect to one another. That means there's no forces causing accelerations or decelerations. If you're on a ship that's pitching and heaving in the sea, then the laws of physics are going to look awfully different to you than they would be on the shore. But if the ship is moving smoothly at a constant speed on a glass smooth sea, and someone else is doing the same experiment on shore, you're going to wind up with the same law. Everybody agreed with that. That was not controversial. It was the second piece of the special theory of relativity that was new. Einstein said, let's take the empirical fact that everybody keeps coming up with the same speed of light and make it a principle of nature. You make it a principle of nature that the speed of light in a vacuum is a constant for all observers regardless of their motion. Whether you're heading towards the ray of light, running away from the ray of light, you're always going to measure 186,000 miles per second. It's counterintuitive. There's nothing else that we know of that does that, but let's make that a principle of nature because it does not contradict experimental evidence. And what follows? What follows is the special theory of relativity, which includes such dramatic conceptual change as looking at space and time as relationships, not things, which is what Newton had defined them to be. From Newton until 1905, space and time, with some few exceptions, were accepted by scientists according to Newton's definitions, that space had an existence, a Euclidean character to it, that existed independently of anything in space, and that time was like an absolute clock ticking away at the heart of the universe at a uniform rate, whether anything happened or not. According to the special theory of relativity, all spatial and temporal measurements, if I measure a length or a temporal interval, that measurement is relative to my frame of reference. If I change my frame of reference, I'm going to get a different number. Knowing the special theory of relativity, I can connect all of these numbers. So the special theory of relativity is a deterministic theory. It's unfortunate that literary people seem to have responded to this theory as if it meant that everything was relative. It only means that measurement of spatial intervals and time intervals is relative to the frame of reference. But all frames of reference, once you know how fast someone is moving, you can make adjustments for it and say, oh, that person came up with a length of 98.7 feet, but given the way they were moving, that's equivalent to our 100 feet in our laboratory. And so there's no surprises there at all. But there is a little surprise. Because if you have a spaceship that takes off from Earth, and it reaches a very, very high speed traveling towards the nearest star. It's reached a uniform speed. And from the Earth, you measure how long the rocket ship is, the spaceship is, and you come up with Well, it's going to be a length much shorter than when it was on the ground. When the spaceship comes back to Earth, corrosion apart, it's going to be the same length that it was when it landed. But time doesn't behave that way. The people on board will have aged less than their twins on Earth. This is sometimes called the twin paradox or the clock paradox. If you put a clock on board that spaceship, when it comes back, it's not going to have the same time as the clock that it was synchronized with on Earth. The explanation for that is that in order to come back, it has to go through a period of deceleration and reacceleration. So forces are now acting on it. So the special theory of relativity, in fact, does not apply to that. You have to use the general theory of relativity to that, and we're going to get to that. So the special theory of relativity required rethinking what we mean by space and time, but perhaps more dramatically, out of plugging into traditional physics, those two assumptions that I mentioned, the principle of the relativity of motion and the constancy of the speed of light, a bizarre equation drops out, E equal mc squared. Now, we may think of atomic bombs, but what's really shattering about this equation is, as I mentioned in the last lecture, the 19th century was tremendously proud of the concept of energy and the science of thermodynamics, establishing energy as a feature of reality parallel to matter. There's a conservation of energy law, there's a conservation of matter law. Now comes an equation which says that the two are really two different facets of the same reality, that matter and energy are interconvertible. You can convert matter into energy and energy into matter. At least that's what the equation says. The equation had no practical significance until the 1930s. Since then, special relativity theory has been confirmed so broadly that it's just a routine tool that scientists use. But there are the two features of the special theory of relativity that we need to pay attention to. One, that it makes all measurement of space and time relative to frames of reference, and therefore it suggests that space and time are not things, they are relationships. And you remember how important relationships become in 20th century science. This is 1905, and they're beginning to emerge here in physics. And second, the relationship between energy and matter. We will soon see how 1905 was a peculiar year for that equation to appear, because it was just 2 years after Marie Curie showed that tiny specks of radium released enormous quantities of energy. Energy that could not conceivably be accounted for by any known chemical process, and so it was speculated that some kind of nuclear energy was being revealed in the course of radioactive disintegration. And E equal mc squared, of course, by the 30 years later, in the middle of the 1930s, the theory of fission came along, which completely vindicated the E equal mc squared, but not with consequences that we are completely happy about. Between 1905 and 1917, Einstein occupied himself with two parallel tracks. One was to develop further his contributions to quantum theory. Concurrently, he also, starting in 1907 in particular, he started generalizing the special theory of relativity. On the one hand, it was not that satisfying to have the theory of relativity limited to the special case of observers that were only in uniform motion. But there was also another problem. See, this is one of the nice things about science, is that very often scientists are motivated by problems. It's the selection of the problem that often is the key to whether a scientist will be perceived as a creative genius or not. You don't start with the solution, typically. The problem that Einstein was concerned with after the special theory of relativity was a peculiar feature of Newtonian science that had been accepted and really unquestioned until the early 20th century. There is such a thing as gravitational mass. We call it weight. That is to say, the effect that gravity has on a material object, giving it what we call its weight. And that comes from the force of gravity acting on the mass of the object. But then there's the inertial mass. That means the mass of the object as determined by its resistance to being moved. If you happen to be an astronaut and you're doing a spacewalk from the shuttle is in an orbit which effectively cancels out the effect of gravity. Gravity is still there, but it's moving in such a way that gravity is neutralized. Any orbital satellite is in that situation. Nevertheless, if you want to move the space shuttle, you can't just push it. The space shuttle has a certain amount of mass, even in a gravity-neutral environment, that resists being moved. That's why you need to have fuel on board. Otherwise, if you could change the space shuttle's orbit just by having somebody hop outside and give it a push, then NASA's life would be a lot simpler. Now, the puzzling problem was gravitational mass and inertial mass are identical, so big deal. Einstein saw that as a problem. Why are they identical? Now, it so happened, not a coincidence really, that an eccentric, aristocratic Hungarian scientist named Laurent Eötvös did an exquisitely sensitive and beautiful experiment and proved that gravitational mass and inertial mass, weight and resistance to motion, are equal to within 1 part in a billion. Einstein said, let's make this a principle of nature. We see a style of reasoning in here, right? He did the same thing with the speed of light in the special theory of relativity. And that's what the general theory of relativity is based on. Let's take traditional mechanics, let's take the traditional rules, and add the equivalence of inertial mass and gravitational mass, take special theory of relativity and generalize it, and what emerges is now a new universal theory of gravity, which is, by the way, still the dominant theory of gravity, a new universal theory of gravity in which space, time, matter, and energy are intimately correlated. Now it's quite clear that space and time are names of relationships, and so is matter, because the mass of an object, although it sounds bizarre, is dependent on, in some way, the total distribution of mass in the universe. If a star winks out of existence through exploding, that doesn't wink out of existence, but a star explodes and distributes its mass over a huge volume of space instead of concentrating it, that has implications for the shape of space throughout the universe. And because what we mean by mass is the relationship between a material object and space, and of course mass and energy interconvertible, so I use the term now to cover both, then the mass is going to change. And we'll get back to that in a moment. So space and time, now in the general theory of relativity, are relationships. They have no reality apart from their connections with matter and energy. If there's no matter and energy, there's no space and time. What was there before? There was no time before. Time and space emerged with the emergence of matter and energy. Space has a shape. Classically, space doesn't have a shape. It's Euclidean, it's featureless in all directions. But relativistic space has a shape. Very famous illustration of this is a taut rubber sheet on which you drop a golf ball. Well, that deforms the rubber a little bit. Drop a bowling ball on it, it deforms it much more. So the shape of space is a function of the distribution of matter and energy in space. The more dense the concentration of matter and energy, the more shapeful space is, the more curved space is. So space has a shape, but space has a shape that it's not infinite. And Newtonian space was infinite. In fact, scientists used to be proud of a fellow named Giordano Bruno, who in 1600 gave up his life, it was said inaccurately, for science because he promoted the idea that space is infinite. But in fact, in the general theory of relativity, space is not infinite. The general theory of relativity predicts that rays of light will bend when they travel near a concentration of mass. They don't really bend. What they try to do is to go in a straight line, but try to imagine a straight line close to the bowling ball on the rubber sheet. You can't draw the straight line. You can try to draw a straight line, but it's going to be curved because the sheet is curved. That's what happens with light rays according to the general theory of relativity. And in 1919, the British physicist Arthur Eddington, part of a team of researchers sent out by the Royal Society of London in order to test the prediction made by Einstein's general theory of relativity during an eclipse, because we can only see stars that are near the edge of the sun, what's called a limb of the sun, during an eclipse. Can't see them during the day. So what you do is you look at a star whose position you know from the night sky, and you compare it to where it is when you see it during the day during an eclipse, and you pick a star that's as close to the limb of the sun as you can get. And by golly, it confirmed Einstein's prediction. Now, an extension of this was actually rather quickly noted by a German physicist whose life was unfortunately taken in World War I, and he was on the Russian front, and he actually made this calculation in the trenches and sent it back home. Calculated that under an extreme case and an extremely dense concentration of matter, the light wouldn't get past it at all. In 1939, semi-independently, the Hungarian-American mathematician John von Neumann predicted the existence of something that in the 1960s was given the name by John Wheeler at Princeton, a black hole, as a region of space in which the concentration of matter is so intense that radiation cannot escape from it. So the general theory of relativity has dramatic consequences, that are still being played out, and we need to talk a little bit more about these consequences. I mentioned the light bending, which confirmed the general theory of relativity, 1919 expedition, and the fact that the theory predicts black holes, which mathematically anticipated in 1939, were actually identified in the 1970s and are now believed to be very widely distributed throughout the universe. For example, current thinking, as we will see in a later lecture, is that every galaxy has a massive black hole at its center. But the general theory of relativity has other consequences that we need to think about. One is that the general theory of relativity is flat out, explicitly ontological. That means a fancy philosophical term for describes reality. It makes claims about reality. It is possible to interpret the special theory of relativity epistemologically. That is to say, as a statement about what we can know, about measurement. Metrologically would be a better term. Metrologically, in terms of what we can measure. So it is possible to interpret the special theory of relativity metrologically, as a statement about measurement. Every measurement of space, every measurement of time is relative to a frame of reference. But in the general theory of relativity, there's no escaping the claim that this is what space is. This is what time is. This is what matter is. Now, the general theory of relativity predicts gravity waves. The general theory of relativity predicts that when there is a change in the distribution of matter in the universe, that waves ripple through space that can be detected and that affect the shape of space everywhere else in the universe. Just as when a star emits a photon, when a star emits light, and we can see it after billions of years traveling through space. I used this example before. If a star becomes a supernova, which is something that stars routinely do in the course of ending their lives. When a star becomes a supernova and it explodes, depending on the original mass of the star, a number of things can happen, and we'll be talking about that too in a subsequent lecture. But the main thing that happens is that the mass of the star is now distributed over a huge area, whereas before it was all concentrated. Now, when that event happens, it sends gravity wave ripples across the universe, which manifest themselves as a change in the shape of space. So, for example, space becomes a little flatter because now it's not a bowling ball anymore. Now the bowling ball has exploded, and what's left is a golf ball and a lot of little fragments, none of which can disturb the rubber sheet much. So now space is much flatter. If space is flatter, dimensions change. They don't change a lot, but measuring length will be different because before, since the space was curved, lengths were, let's just say, shorter, and now they're going to become a little bit longer. No one has ever detected, well, no one has yet detected gravity waves. There have been a number of attempts to do so, and at the end of the 20th century, the National Science Foundation funded the construction of America's first gravity wave telescope, which is based on Michelson's interferometer. It is a device which is several miles long, which is capable of determining a change in the distance between two fixed points as small as the diameter of a proton. The next time a star explodes in a region that this instrument is sensitive to, then we would expect to see some kind of a change in the shape of space in the immediate environment of the Earth. And if this instrument isn't sophisticated enough and sensitive enough, NASA and the European Space Agency are collaborating on a space-based interferometer in which the legs are millions of miles apart and which would be able to detect changes in space much smaller than that, 10 to the minus 16 centimeters. So scientists take very seriously the prediction by the general theory of relativity that there are such things as gravity waves, which would propagate at the speed of light and, in fact, would have to be carried by something called a graviton, analogous to a photon. That is, to say, the carrier of gravitational energy should be the kind of a thing that a photon is. Photons carry electromagnetic energy. Now comes, in a certain sense, the most amazing prediction of the general theory of relativity, and one which Einstein himself could not believe. And so he modified the theory because he thought, surely the theory can't be right if it predicts that. In 1917, a Dutch physicist named Willem de Sitter wrote to Einstein, right? This was only 2 years after the general theory of relativity was published, in which he showed Einstein that certain solutions to the equations that he published for the general theory of relativity implied that the universe was expanding. And furthermore, it actually implied that under quite realistic assumptions, the expansion would be accelerating. Einstein was quite well aware of the fact that contemporary astronomers did not believe that the universe was expanding. There was not the slightest shred of experimental evidence that the universe was expanding. And so Einstein, between 1917 and 1922, kept going back and fiddling around with his equations, introducing a term to eliminate the expansion of the universe, because there ain't no expansion. Now, of course, the great irony is that perhaps the single greatest scientific discovery of the 1920s is that the universe is expanding. For decades after, Einstein used to say, it was the dumbest thing I ever did, playing around with my own theory to make it right. And it's also very revealing and interesting about Einstein as a character, because in other respects, Einstein was not bothered by whether experiments confirmed his theories or not. I mentioned earlier his 1905 paper on the Brownian motion. In 1905, Einstein's theory of the Brownian motion did not, as a matter of fact, match current experimental evidence. And in 1906, he published a follow-on paper in which he mentioned this divergence, but said he was confident that future experiments would vindicate the theory, which they did. And yet here, well, maybe it's age. Here it is, a mere 10 years later. And Einstein, well, if the astronomers say it's not expanding, then I guess I have to modify my theory. So the general theory of relativity has cosmological implications, that space is finite. The universe is expanding. If it's expanding, then it's finite in time too, because it means it had a beginning. And that space, time, matter, and energy are intimately connected. We are going to stop for the moment and not follow the cosmological consequences of the general theory of relativity. We will reserve that for a future lecture, and we're going to turn to quantum theory for two reasons. First, because Einstein himself was one of the architects of quantum theory. And second, because in the 1980s and 1990s, physicists have been attempting, since the 1980s and 1990s, physicists have been attempting to unify quantum theory and the general theory of relativity. And so we'll pick up on that theme. Thank you.